welcome to this PSE Dean's Distinguished Seminar by Professor David Pui. Let me introduce Professor Pui. He's a Regents Professor and L.M. Fingerson TSI Chair in Mechanical Engineering at the University of Minnesota. He's also a member of the U.S. National Academy of Engineering and the director of the Center of Filtration Research. I think he will talk more about it, which consists of 20 international filtration manufacturers. Professor Pui has a broad range of experience in aerosol and nanoparticle engineering and filtration technology, and he has developed a number of aerosol instruments that are workhorses in every single aerosol laboratory. Okay. He has also developed large-scale urban cleaning systems, and he will talk about that, India, China, etc. So he has received a number of awards, to just name a few. The Max Planck Research Award, the Chinese Academy of Sciences Einstein Professor Award, and all senior level awards in the international aerosol community, in particular the Fuchs Memorial Award, which is given maybe 2 awardees once every 4 years. And that is the highest disciplinary award in the Society of Aerosols, joined by the American, German, and Japanese Aerosol Associations. And he has served president of American Association of Aerosol Research. On a more personal note, I know David when I was in graduate school. So he spent half a year at Caltech doing sabbatical, and he has been very generous, even though I'm not his PhD students, he has been very generous to serve as mentor for my academic and professional growth, and of course, research ideas. So thank you so much. Welcome to KAUST. So please join me in welcoming Professor David Pui.
Thank you very much, Dean Jack Chan. Yeah, we have a long history of collaboration. I appreciate that you invite me to here to share my recent research results. So, I would like to talk about green technologies for sustainable environment. I'd like to start out with quoting Lancet Commission. You know, Lancet is one of the top 2 medical journals, saying that pollution is the largest environmental cause of disease and premature death in the world today. 9 million premature deaths is caused by pollution, and of that, 6 million is caused by airborne pollution. And in some country, more than 1 in 4 of the premature death is due to pollution. So with that in mind, I set the goal for my research group to develop green technologies that benefit sustainable environment, which will enable people and the environment to prosper together. So there are 3 objectives. One is mitigating PM 2.5 volatile organic carbons and ozone in urban environment. Second is to reduce CO2 to mitigate global climate change. And third is to provide clean water to achieve water sustainability. Now, I should say that our laboratory has been involved in instrumentation development for a long, long time. I'm the 3rd director of the Particle Technology Laboratory. And here are a few of the instruments that I developed. In fact, this first one, the differential mobility analyzers, I developed that during my PhD thesis. And now TSI is still selling it. Probably there are 10,000 of this around the world. And then more recently, my student and I developed a DMA fitted for nanoparticle size range. And if you were to put them on this platform, which control the flow rate and the voltage in the DMA, and then the extracted aerosol go to a particle counter, this becomes the scanning mobility particle sizer, the most important particle size distribution measuring instrument in the world. There are several thousands of this sold around the world. And this two more recent development in measuring particle surface area. I will tell you a little bit more about particle surface area. Now, as a result of our work developing the instrument, prior to the DMA, there's very little information in the submicron particle size range. Now the instruments are developed, worldwide researchers measure that. It turns out that atmospheric aerosol consists of two modes. The first mode, now this is volume distribution as a function of particle size over 5 decades, particle size of interest. This is 0.01 micron, 10 nanometer, 1 micron, 100 micron. So we find that the atmosphere consists of two modes, fine particle modes and coarse particle mode, with a break at 2.5 micron. Now, I will tell you a little bit more about the less than 2.5 micron. Those are formed from anthropogenic man-made activities. So here's more details showing that you can think of PM 2.5 micron is here, less than 2.5 micron. Those are from combustion gas to particle conversion. So coming from power plant, engine emissions. Now they have extremely long lifetime from days to weeks. So they can transport over a great distance of 100 kilometers, actually thousands of kilometers away. So Korean complained that the air pollution in Seoul comes from Beijing. That can be true because the PM 2.5 can travel that far. Whereas for the larger than 2.5 micron, those are from windblown dust, construction activity, agricultural activity. Those are big particles, so they settle very quickly, and their lifetime is only a few hours. So they rarely transport over 100 kilometers. So with that in mind, in consultation with our lab, US EPA set the PM 2.5 standard. Now you see that 2.5 is a subscript that is less than 2.5 micron, and the 24 hours standard is 35 microgram of particle mass per cubic meter of air. And for annual average should be 12 microgram per cubic meter. So remember, 24 hours, 35, and annual, 12. I will test you later, okay? And so my research also are the basis of several important standards. First of all, I work with George Mulholland at the National Institute of Standards and Technology into certifying the 60 nanometer, 100 nanometer primary particle standard that's traceable to the 1 meter rod. And using the DMA technique. And here are ISO standard, the first one on particle size distribution measurement using the DMA technique. Second one is calibration of aerosol concentration, number concentration. Now this technique, actually I developed it during my PhD thesis, but recently there's a lot of citation. The reason is that in Europe, the Euro 5 and 6 vehicle emission standard now is based on number concentration. Previously, the concentration is mass concentration, but now engine is getting so clean that you can not measure the mass too well. So whereas number concentration can bring the sensitivity of detection several order of magnitude lower. So therefore, any instrument used for measuring particle number concentration, they will need to use this method that I developed many years ago. And so there's a lot of citation on this paper, particularly recently. And then the third one, I work with my former postdoc, now professor at ETH Zurich, into measuring the efficiency of air filtration media in the nanoparticle size range. Now, you will see that PM 2.5 is in the nanoparticle size range. Typically, we call it nanoparticles, maybe 10 nanoparticle to 100 nanometer. Those are the technical nanoparticles that you deliberately make it for nanotechnology development. So because nanoparticles are the basic building block of nanostructure material, here are a few of this nanostructure material. Carbon black consists of, the tire consists of 30% by weight of carbon black. Those are actually agglomerate coiled together like a spring. When the tire bounces around the spring, just stretch and recoil and so on. A good tire is one that has the right nanomaterial of the right size. And TiO2 used in paint. So you would like to make the TiO2 particle about the visible light wavelength range, so that after you paint the wall, the light shine on the wall will be reflected out in the wavelength of light. That is, you will see the reflected light well, so that one coat of painting is good enough. But if you use the wrong size particle size, then you can see through the TiO2 particle and inside the background color. And then SiO2 used in optical fibers and also flowing aid and cosmetic products, and zinc oxide as vulcanizing agent for toughening the rubber, and then nickel for batteries. So they are, like I mentioned, consist of nanoparticles. And so with nanoparticles, it will create a lot of surface area. So this is an example of how powerful it is to create surface area. Now, if you look at the soccer ball and the 10 nanometer particle, the ratio is 10 to the minus 8. And then the Earth diameter to the soccer ball diameter is also 10 to the minus 8. So that means if you were to make enough 10 nanometer particle to stuff the soccer ball, you create as much as surface area as creating enough soccer ball to stuff the Earth. So just imagine how much surface area is introduced. You know, chemical reaction is surface area based. So that's why in the case of PM 2.5, those are the bad particle affecting your health, and they are in a nanoparticle size range. That's why they are so toxic. However, if you were to produce good nanoparticles, such as what we have done in using electrospray technique to produce nanomedicine. So my former student and I, actually we teach people how to do it. We published these two papers, and there are 1,000 citations on these two papers. So you see that there's a metal nozzle. We run water through the nozzle, and initially it's bigger droplet, and millimeter size. And then you attach a wire and applying high voltage to the nozzle, and you continue to increase the voltage, and then it will pop into cone jet mode. And sometimes they call it Taylor cone. And at this mode, you see the meniscus become a cone, and the liquid come out at the apex. And so particle produce a nanoparticle size range. And if you are smart and can produce a lot of quantity of that, we actually filed 12 patents and form a company, Nanocopier. And recently they told us that FDA has approved the license for the company to produce a major cancer drug. And I understand that it's a $2 billion cancer drug because in medical tests, they find out that nanostructure medicine has much higher efficacy than the normal formulation. And then they also told me that another second drug is being approved by FDA in the coming year. Now this is another application of nanoparticles, but semiconductor also is very careful about nanoparticles. So here's a project funded by Intel many years ago, and they want us to look at contamination produced for extreme UV lithography, the last top-down technology. So you see that you put image on a fused silica substrate, and typically in normal lithography, you can put a pellicle above that sensitive surface, and if there are particles, they will deposit away from the sensitive surface that print the image. However, for extreme UV, you cannot put a pellicle over that because the pellicle screen will remove a lot of radiation. So they do it without a pellicle. Now, if there's a contaminant particle, it goes right into the image and causing defect. So if you print using this pellicle, you have a lot of chips that you cannot use. And so we published 16 papers on how to prevent contamination. I'll show you one example later. And some of our students become Samsung VP, LG Display Senior VP, and so on. And now here's the protection schemes that we propose. First, let's say that this is a pellicle or a lithography plate inside a container, normally under high vacuum. And then you can put a cover plate to prevent particle from settling. But better yet, you can turn it upside down, so settling will help you to prevent particles. And then you can put electric field. That's not enough, that's not good, because if you have a particle with the opposite charge than the voltage on the plate, or on the mask, then it will attract particle actually. So we use temperature gradient. It turns out that only a few degree higher temperature on the mask will be sufficient to prevent particle from push the particle away. And this become, we also put in a particle trap on the side. In that case, even electric field can be used because the particle electric field can be deposited on either surface here. So we have graduated a whole bunch of students, and my former lab manager, Dr. Kim, is now the key contamination specialist at ASML. That's the main EUVL company. And Dr. Yang Yi He is the Senior Director at Applied Materials, which is the largest semiconductor manufacturer in the world. And he also developed PV cluster tools to make a PV plate. Basically, for making PV plate, it's just like making semiconductor plate. So you need to go through many processes. So he put all the deposition chamber and etcher and all that, surround it in a circle, and then the plate can go in and out in a very efficient manner. Nowadays, PV screen panel can be produced like every few seconds you can make one, thanks to some of these tools. Now, I should also mention that I'm fortunate to have 20 companies supporting my research, Center for Filtration Research, and the company consists of major US company, 3M, Boeing Commercial Airplane, Paul, and Applied Materials, and then Korean company, Samsung Electronics, LG Electronics, and Chinese company, my dear, Xinda, Huayuan, and then German company, Mann+Hummel, Freudenberg, and Japanese company, Shigematsu. So truly international consortium. They produce 50 million annual sales a year with application in removing PM 2.5, contaminant, engine emission control, cabin air filter for automobile airplanes, respirator personal protection. Now, at any point, we are working on 15 different research projects, so it's not possible for me to give you the complete research project we are doing. But I should mention that our member company suggests the state-of-the-art topic for us to work on. So we just add to the bottom here, the red color, and then we continue to work on it. When it's done, it becomes black color. So keep on adding on the bottom and getting work done. So like I mentioned, there are 15 projects. I just pick a few to show you what we are doing. And electric filtration is very important technology because it can achieve high filtration efficiency with low pressure drop. So typically in filtration, you have a fiber going into the wall, and then your flow streamline around the fiber. And then when you have particle flowing very close to the fiber, can be intercepted. When you have a heavy particle go in a straight line, impacted. And then when you have tiny particle diffused by Brownian motion to the fiber. And then if you charge the fiber, you have the charge can attract particle to the fiber. And so here is a demonstration of mechanical versus electric filter media. Now, typically, mechanical filtration consists of fiber and a particle depositing on the fiber by mechanical interception, diffusion, and so on. Now, so this is for the mechanical filtration. You see that it's effective in collecting very small particle, and larger particle collect by interception and impaction. So it's a V-shaped curve. However, COVID-19 single particle is 120 nanometer. Efficiency is less than 20%. However, if you now put charge on the fiber, and then efficiency went up all the way to 80%, and actually the pressure drop is lower too. That's why here are the respirator we evaluated during the COVID time. Most of the high efficiency one, the blue shaded region, they are all electric media. Mechanical media are the lower ones. And every spring, I teach a big class, and everybody's wearing masks. And we also do modeling of cleaning of the classroom, and by considering outside air coming in, inside air recirculation, and installing indoor air cleaner. And then we publish this web-based software on an open site, so everybody can use it. The facility management used it to evaluate 800 classrooms in Minnesota, and buying 500 indoor air cleaner to put into the older classroom. And they said that U of M, Minnesota, has the lowest infection rate in Big Ten university. Hopefully, what we've done has add some value to that. Now, recently, we work on a small, user-friendly bioaerosol sensor. Now, this thing is actually, can be handheld, very small, and you see a laser beam going across here, and a camera looking at the scatter light, and then the airflow going through here like that. And along the path, we insert a filter that will cut out the dynamic light scattering. Dynamic light scattering are the light scatter that has the same wavelength as the illuminating laser beam wavelength. So here we use a blue laser with a wavelength of 400 nanometer. So all this 400 nanometer signal. And then in here, we install a filter to cut out all those dynamic light scattering signal. And so here, we only measure the induced fluorescence, and in this case, the wavelength is 600 nanometer. You see that on the right-hand side, you detect every particle. On the left-hand side, you detect only bioaerosol. And here's a convincing demonstration that we have sodium chloride, non-biological, and the biological here. And here we look at the elastic light scattering. Both sodium chloride and bioaerosol show visible signal. And then we put in a screen to cut out the wavelength around 805. And so only induced fluorescent particle are detected. So you can see that this sodium chloride has no signal. And this one, there's strong signal at 600 nanometer wavelength. Those are the bioaerosol. And recently, too, we used the color to distinguish the particle. So this bioaerosol is green color, and other bioaerosol is purple color. So if you look at here, you can see the different color, green color, purple color. That's a way to distinguish what type of bioaerosol you are detecting. And then one of my former students, he started a company to make medical robots. So these robots go around the hospital to look for bioaerosol. So I propose to put our bioaerosol sensor here, and when it detects bioaerosol, pop up the UV disinfection tube to disinfect that area. So hopefully, actually he already has good success even without my bioaerosol sensor. So the next topics I'd like to address is how do you clean up the urban pollution, including CO2. Now, we have worked on indoor air cleaner for local control, the gasoline particulate filter for source control, large-scale air purifier, I call it solar-assisted large-scale air cleaning system, SALSCS, sources for urban area control. And then CO2 is a second generation sources which can use to reduce CO2 to reduce climate change. And if we can do all of this well, you will agree that we will create a sustainable environment for the world. So air pollution is very bad, particularly in India now. This is a screenshot of one winter day in Delhi, and their PM 2.5 is 500 something. You know that the EPA 24 hours, do you still remember, what is it? 35, yeah. So it's 12 times higher than the EPA standard. And so the minister said that we are living in a gas chamber. So WHO said that 1.67 million deaths happen in India. Health effect of PM 2.5 is bad. It causes lung diseases, heart diseases, coughing, wheezing, short-term exposure, heart attack, and then long-term asthma in children and cancer. So the landmark study is done by Harvard 6-city study. Here are the medium-sized city. They plot the PM concentration as a function of mortality rate. And you see that from 12 to 30, the death increased by 30%. Now, in 2014, the PM 2.5 in Beijing is 125, so way, way up. And now, with investment of $26 billion US, Beijing now reduced to about 35. But still, you see that they can save a lot of life if they continue to do it. Now, I also checked this 6 cities. All of them are below 12 now, the standard. Because if your city is higher than 12, EPA can come in and shut down some of your factory. So we thought of the idea, this is 10 years ago, of using this solar-assisted large air cleaning system, sources, to take out the PM 2.5. Now, the original modeling is a huge tower, 500 meter high, and the base is 5 kilometer diameter. So the calculation modeling showed that we can remove 22.4 cubic kilometer in 24 hours. So now it operates by having this shroud, is glass panel that tilting higher towards the middle, so that when sunlight comes down, it will heat the air below the glasses, and when the air is heated, it will rise due to buoyancy, and then rush towards the middle and come out. And then before it come out, there's a filter system to remove all the PM 2.5, so only clean air come out. So in this modeling, using weather research and forecasting model, we put 8 of them around Beijing city, and in 2 days, PM concentration reduced by 15%. Now we published a total of 7 papers on this type of technique, so we have a lot of experience on that. Although the large-scale system will cost a lot of money, so it's not easy to convince government to do it. However, we were able to build a couple pilot-scale unit with local government support. This first one is built in Xi'an. Now, it's only 60 meter high. The original one is 500 meter high. So, and the base is only 50 meter. So we are talking about the scale of 100 to 1. smaller unit. And you see the glass plate tilting higher towards the middle. So it's drawing air from the surrounding and then into the opening in the chimney, and then to rush the air. Now along the way, there are some filter to remove PM 2.5, and so the only clean air coming out. Now, over the year, we built one unit in Xi'an, one unit in, we call it second generation in Yancheng. This one is capable of doing CO2 scrubbing as well. I will tell you more. And then 2 units in Delhi, India. They have the worst pollution. And this attracted a lot of attention. There's a Facebook posting with a lot of viewer comments, and most people thumbs up, saying that China is the world's largest air purifier. And there are 1,000 technologists from around the world to look at it. And India pays special attention. They invited me to give Diamond Jubilee Distinguished Lecture at IIT Bombay and IIT Delhi. And then they took me to see their Minister of Environment. So after that, they decided to build 2 units. Now, 1 unit is built in a transportation hub. This is railroad. This is this is subway, and this is bus depot. So a lot of people, 100,000 people walk around here all day long. So we cannot have the air going up and clean air going up. We want to push the clean air to the surrounding so the pedestrian can have cleaner air. So we do it inverse, pushing the air from top, and then use fan to blow the clean air out. And these are the pleated filter, and then fan blowing it out. So there are 2 unit built. This one is a transportation hub. This one in a commercial center. You see that this clean air delivery rate is 3 million cubic meter per hour. So it's providing a lot of clean air. And New York Times took a picture of that. Next, I want to address the climate change issues. And all of you know that climate change causes temperature rise, sea level rise, hydrological extreme in droughts, flood, and fires. And health effects include heat stress, respiratory disease, malaria, cholera, malnutrition, large-scale migration. Now, it costs a lot of money to fix the health effect, whereas technology can reduce the cost significantly by removing those greenhouse gases. And this is what we are doing in the second generation sources built in Yancheng. Here, instead of using filter, we spray water droplet to take out the PM 2.5. When water droplet fall, it will capture PM 2.5. Although the efficiency is not so high, filter, you can easily do 95% efficiency, but for water droplet, maybe 60% efficiency. Anyway, we published the paper in here. However, we can put sodium hydroxide in the water so that you have sodium hydroxide droplet produced, and that can take up the CO2, turn it into sodium carbonate. And then you see that there's a drain going into utility room where CO2 can be sequestrated, and then sodium hydroxide recirculate. So now this technique of using sodium hydroxide is not new. Actually, American Physical Society, they proposed to set up 1 kilometer by 1 kilometer farm with many contact tower, dripping sodium hydroxide solution, and then use fan to blow air towards the contact tower. And in economic analysis, they said that no way, as the electricity required, you are trying to blow the whole world's air through those contact towers, so requiring a lot of electricity. So So they abandoned that. However, for us, remember the Beijing source is a huge one. We don't use any electricity. We actually use sunlight to heat the air to move large amount of air. So it's totally feasible for using our technique. Now what happened with the CO2 you harvested? You can, my colleague, he has a DOE project of pumping it down to the cavern, warm up the CO2, bring it back up to run a gas turbine to generate electricity. So now I have a proposal for Saudi Arabia as I look at the Saudi's commitment to CO2. Now, Saudi Arabia has committed to capture 44 million tons of CO2 per year by 2035, you know that. And however, if we were to use 10 of those giant towers and operating it, we can remove 16 million tons of CO2 per year. That's 1/3 of Saudi Arabia's commitment. So we can actually help Saudi Arabia fulfill the commitment much earlier than 2035. We can build 10 towers in 3 years, for example. And additionally, the shroud, originally we used glass plate, but we can replace it with PV panel. Nowadays, like TCL, they have transparent PV panel that the sunlight still can go through, but meanwhile, it can generate a lot of electricity. Remember that the shroud is 5-kilometer diameter. So I estimated that 10 of those can probably generate sufficient electricity to run the whole Line City that NEOM is considering building. And and then the captured CO2 can be pumped underground into the deep reservoir. Saudi has a lot of well that is empty, so you can pump it down there, and then you can bring it up to run a gas turbine if needed. So more electricity. And now we have 4 sources unit built in China and India with 7 published papers on modeling by us. So we have a lot of experience, and I feel that there's a good chance for the success of this project. Actually, this morning, I talked to Professor Ian Campbell, and he liked the idea. And we will arrange to talk to NEOM, I think, in a couple of days. And so they are building this Line City, which is 500 meter high. So our tower is 500 meter high, so it's very compatible. So they have technology to build it. Now, the other idea that I have thinking about coming to Saudi Arabia is to the dust storm. You know, Beijing has dust storm, and it comes from Inner Mongolia. They can identify several areas in Inner Mongolia as the starting point. So 10 years ago, my postdoc, Jing Wang, and now he's professor at ETH Zurich, and I wrote a paper. So we proposed to build a great wall of solar panel, stretching maybe 100 kilometers, very tall. And during the sunny day, is harvesting energy, and during the beginning of a dust storm, it shut up to become a great wall of panel to stop the dust storm. Recently, I also have the idea that, you know, that actually Professor Chek Chen and I, we have a patent on this, that in the freeway, there are a lot of emission exhaust. We can draw the emission exhaust out, and then to ducting the dirty air to a dust collector and bring the clean air on the other side of the freeway, so that it cleans up the freeway air. But in the meanwhile, if you were to use this idea to put it on the side, like a lot of freeway, they actually have sound barrier. You can replace the sound barrier with a PV panel, and in the daytime, harvest energy, in the nighttime, shut down to avoid noise pollution. And and I understand that there are more than 10 kilometers that can install that. Maybe we can put it on the wall. And then, you know, the line, I just took it from a video. It's very long, 500-meter tall buildings, and many linked together to form many kilometers. So we can put some of this panel idea around there. So anyway, in conclusion, I'd like to say that we have performed fundamental and applied research towards developing green technologies to mitigate PM2.5, purifying clean water, and reducing CO2 in the atmosphere. Our goal is to create a sustainable environment which will enable people and the environment to prosper together. You know that as a professor, our main product is to produce students that do very well to continue on what we start out doing. And here are some of the students: chair professor in Taiwan, chair professor in US, director of NIOSH, vice president of Samsung Electronics, senior vice president of LG Display, senior director of applied material, professor. There are many in Korea, Switzerland, and so on. So, oh, there's one in here. Oh, did I miss him? Professor Zhang Xiang, president, huh? Is there?
The fourth one.
Oh, here. Xi'an Zhang is president of the University of Hong Kong. So I'm happy that he spent a little bit of time in Minnesota with me. Now, I always like to finish my talk showing this slide. You know that this is in Forbidden City during a smoggy day. And I like to superimpose this progress wheel of PM2.5. Now, this wheel is driven by 3 gears: academic gear, government gear, and industry gear. Academic are good with identifying sources and effects. And when the pollution is bad, government come in and set strict standards for ambient and vehicle emission. And then industry, such as our CFR, can develop backhouse emission, diesel, gasoline particulate filter, and then that will then reduce the source. So what we like to do is to have this 3 gear to turn in the same direction and same speed. And then that will turn the progress wheel. Let's see if it works. Aha, it's turning. So guess what? After a few turns, you discover the Forbidden City without smog. How do you like that? Good? And I should mention that people always ask me, what is this gear in the middle? Actually, if you're a mechanical engineer, that's a sun gear, that's a planet gear. So you see, without this gear, this turn this direction, this turn the wrong direction, lock up. So this is an extremely important gear. So what is this gear? Is Todd, is Chan, is all of you and me. We encourage the 3 gear to turn together. And so the community is asking the 3 gear to collaborate. Okay, so I think I stop here and just show you the Now remember, this is a miniature of what I proposed for Beijing. This is 1/100th the size of the giant unit. And so in Xi'an and guess what? One of the economic professor in Jiao Tong University, he went and surveyed a lot of this building around the tower. They find that people are willing to pay 4.5% more in real estate value to live close to the tower. So this is another benefit. Okay, I better stop here.
Okay, let's thank Dr. Pui. Thank you so much.
Okay, thank you.
And we have time for a few questions too. Turn the time over to you guys for a minute. Yes.
Thank you, Professor, for your talk. This salsas technology I found really interesting, really impressive. I liked it a lot. I have a few questions about it. Particularly here in this video, it showed that at night there's some lights on top. I'm wondering if they have any functionality or if it's just for aesthetic.
At night, which slide?
On the video and also on the...
Or on the video. Yeah, at night, whether it operate or not, yes. Actually, it turns out that we put pebbles below the glass panels, so the sunlight heat the pebbles in the daytime, and nighttime the pebble emit heat and warm the air. So at night, the flow rate is about 50% of the daytime. So it's continuing operating. Yeah, you have good observation. Yeah.
Okay, thank you. My next question is regarding this, probably because I don't know about this field of science. For the CO capture, you mentioned that you pump the CO to underground.
CO2.
Yes, CO2. No, sorry. Why is that? Why not store it in the surface and do this process on?
Yeah. So, because my colleague has a DOE project to demonstrate that he can do it, and I was thinking that in Saudi Arabia there must be a lot of oil reservoir that's pumped dry, and it would be a good place to store the CO2. And recently, I also talked to some chemists. You know, there are some chemists that convert CO2 into ethanol, biopolymer, to make good product out of that. So we are looking into that. But when you're talking about those 10 units operating, you're talking about a lot of CO2. So the easiest way just to put it into the ground.
Okay. And finally, if I may, just on the slide with the Harvard 6-city study, there, you know, anything that's related to sociology, because you compare the quantity of particles to mortality rate. Slide 24 or 29, I'm not sure.
This row?
29. No, on top.
The Harvard 6-city study.
Oh, okay. Yeah.
Yes. So and you also mentioned that these cities, they reduced the PM 2.5 concentration, but I'm wondering, did the mortality ratio decrease as well? And I'm wondering this because, like, on every sociological study, there's a lot of factors.
What they do is to set P. P is Portage, Wisconsin, very close to Minnesota. It's quite clean. As the marker. So they compare the death rate in this city with the Portage, Wisconsin. And then they do have PM 2.5 value for each city. So then this is how they plot it.
Yes.
And people always suspect, how can health effect curve be so linear? So there are a follow-up study that demonstrate that it works. And I mean, that the value is correct. And the follow-up study also show all the city moving to the left and saving a lot of life, yeah.
Yes, but so my problem with this graph is that mortality ratio can be influenced by many other things, right? And especially because it was done in the 90s, the study, we don't know if, or it doesn't mention on this slide if there was a peak in the crime rates in the city all the way to the right. And so I'm just, it makes me skeptical if I don't see all the other factors, you know, because in sociological studies, there's always this to calculate the mortality ratio. But I do think that it makes sense that there's this, that the concentration of particles. So I agree with you. I just don't fully believe this graph without more information.
Yeah. There are a lot of publication on this study, and so if you go into there, you can see the whole. Actually, they have done follow-up study in the 80s and 90s, and it's the right curve. But what is worrisome is that in Delhi it's 120. So who knows where we go? So as aerosol scientists, we can help save a lot of lives. I mean, we're talking about 1.6 million deaths every year. Yeah.
Thanks a lot again, Professor.
Yeah. Thank you. Yes.
Here you go, Benny.
Okay. Yeah. Thank you for the nice talk. And well, I can appreciate we have a lot of these instruments that you invented in our labs here at KAUST, like a DMA, SMPS. So thank you for your contribution there.
Thank you.
And well, you said in CO2 we have plenty of oil reserves that are empty. Actually, all the reserves are full of oil in Saudi. That's the national message, okay?
Oh, okay.
So there's no empty reserves of oil.
Okay.
But we have still plenty of place to store CO2.
Okay.
But that's not where the oil is.
Okay.
And we have some projects here at KAUST.
Okay.
Professor Volker and Thomas, they're doing the CO2 geothermal work.
Yeah.
So very much aligned with what you...
Thank you for telling me that. In Tompkins' work, he's talking about pumping it 7 to 8 kilometers underground.
Yeah.
So it's below the oil reservoir. Yeah. So in fact, US EPA actually identify some of the location for storing the CO2. Let me see if I can find it. Oh, here. So all those blue are the area that DOE has identified that can store the CO2. So there are plenty of locations in the world that can store the CO2. Yeah.
So I want to come back to the concept then of the capture of the CO2 using the sodium hydroxide. So my feeling about this concept is the challenge is primarily around recovering the CO2 from the sodium carbonate. So you'll have to have some type of caustic cycle to remove the CO2 from this, which is absorbed into the sodium hydroxide, right? Mm-hmm. And that's typically a thermal treatment, which requires a lot of energy. And so to me, that's the challenge in this cycle is not the capture of the CO2, it's the recovery of the CO2 from the carbonate.
But remember, the shroud with PV screen can generate a lot of electricity, more than enough to do whatever is needed. Yeah.
Have you done the calculations for that part?
Yeah, I did some calculation. Yeah. One tower can support maybe 1 million homes, something like that. So it's a lot of energy. Yeah.
Okay, thank you so much.
I should mention that the American Physical Society, they published a manual on the physics of sodium hydroxide chemical reaction and how to do it. So the only thing is that at the end, they say it's too expensive, but then you can get a lot of information in this manual. Yeah. Mm-hmm.
Okay, well, thank you so much, Professor Pui. We're so glad you came today. And let's thank our speaker one more time.
Thank you.
If you want to meet with Dr. Pui, there's probably still a little bit of time left, but he has a pretty tight schedule, so come see one of us. Thank you.
Oh, yeah, I typically try to take a picture of my audience. Can you wait just 1 second? Oh, maybe you can take it with me standing here too. Sure. Okay. Okay, thank you.